Okay, last call for homework. Anybody else want to hand in homework? Ready to get started? Today is 20th. We're starting chapter 11. The homework you just handed in was from chapter 9. And when's our next quiz? The 29th? What is that? Thursday, obviously, huh? Which is good. Now, we're moving on to chapter 11. I think last semester that I figured out a way to break the chapter down into certain parts and certain ways to make this chapter easier, because I've always heard that this is one of the hardest chapters of the semester. So what I did is I put in all parts here so you know what to expect. If there's any lectures you want to attend or make sure you watch, it's going to be this chapter. There's a lot of students, I don't know, find this hard. So here's how I broke it down. You're only going to learn 4 waiting line models. And every one of the 4 have Poisson arrivals, meaning, you know what, I want to start over. Because I want to make sure you understand what waiting lines are all about. If you're managing, you get into a management position at a business that has a waiting line, it might be something like you work at a bank or a credit union and people have to wait in line to get to a teller. You work at, you're a regional manager for a Walmart and everybody has to get in line to cash out. You're working at, you're managing 4 or 5 different theaters and people have to get in line to buy their tickets. Anything where people have to have a wait to be provided some service, check out, pay for something. You know, in the old days, I almost said gas. I can, you know, I'm so old, I can remember when people would come out to your car and pump your gas for you. I know probably most of you have never even seen that in your life. Anything you can think of. If you have to drive up to a car wash and you got to wait for the car in front of you to get finished before you can pull in, that's a waiting line. Any of these types of businesses, this is where this comes in handy. And what it does is, I like to use the credit union as an example because I used to audit credit unions, is that, you know, you're working at a credit union and next thing you know, you become manager of all the tellers, the drive-through, the in-house, maybe more than one location. And where you're going to earn your pay as a manager of tellers is where you are scheduling the exact right amount of tellers at each branch based on the historical amount of customers that arrive during certain time periods. From the time you open, you might break it down, a lot of them break it down to 2-hour or 4-hour shifts. And they'll say, okay, I'm going to do my scheduling where I have the perfect amount of tellers from the time we open until 3 hours later or 4 hours later. And then I have a switching tellers where I have now this many from this time to another 4 hours. And then we're open for maybe 3 or 4 more hours, so I'll have this. And they work out schedules like that because certain times of the day they can look through past of how many transactions took place, meaning how many customers arrived, and figure out the perfect amount of tellers to have. Now, what does perfect mean? That's where all these formulas come in. The perfect amount is where you're meeting certain criteria. If the cost of somebody walking into this credit union or bank that you're managing the tellers, and they look like, or they end up waiting too long, and if they end up waiting so long that they want to withdraw all their money and go to the credit union that's just down the road because you got competition everywhere, then that means you misscheduled. That somebody shouldn't ever have to wait that long. But on the other hand, you could accidentally schedule too many as an overkill because you never want somebody to have to wait too long, and then you're wasting money. And that's what these formulas do, is find that exact point to where you're scheduling the exact right number, to where you're not wasting money and not risking losing customers. It's that balance. And it all comes down to that balance. We're going to learn that one of the most important parts of this is called the economic analysis. And this economic analysis can be completed and computed no matter which one of these 4 methods we're going to use. Now, there's more than 4 in the book. We're just going to learn these 4. You're going to get into more of these in operations management and more in depth. I'm just introducing you to it, so I'm sticking with these 4. Now, the hardest problem you're going to have when you're taking your quiz related to Chapter 11 is you're going to read a problem and you're going to go, okay, which formula do I use? So I'm really going to highlight how you determine which one you're reading about. And that's why I have them all listed here, because I'm going to give you hints on every one of these 3 lectures as to this should lead you to this formula, or that one, or that one. So all 4 of them have arrivals that are following what's called a Poisson distribution. You know, you can't predict exactly how many people are going to arrive, but you can look at historically on a Tuesday from 9 a.m. to noon, how many have arrived. The last, you usually pick a random 30 of them, and you'll use those 30 Tuesdays from 9 to noon, how many arrived, and you can come up with an average of what to expect then next Tuesday, or the following Tuesday, unless there's something special about that day. If there's something special about that day, you may have to look at that exact day over previous years to see how many arrived, to give yourself a good idea of what to expect. And then you schedule accordingly. So they all have Poisson arrivals. These 4 differences are on how the service takes place. Exponential service, single channel. The single channel means there's only a single service station. Like most car washes that are automatic, it's so expensive, there's only one automatic car wash there. So when a car pulls up, it's single channel, because if it gets busy, and you can see on a sunny day when finally spring really does hit it, you'll see cars lined up to get washed at an automatic car wash. And that's a single channel, because there's only one automatic car wash they can go through. Yeah, there's the manual ones, but I'm talking about an automatic. So that would be a single channel. Multiple channel is when there's more than one service, like the credit union bank. Usually there's multiple tellers that could help and provide service to customers. So that would be multi-channel. Constant service. This one means, and it's constant service, single channel. And this one means that whatever service is being provided, the exact amount of time it takes to provide that service is the same for every customer. And almost always, when you read a problem that has to do with constant service, the service is being provided by non-human. Because it's the human that can't be constant. So, if, for example, that car wash I'm talking about only provides one type of wash, it's going to be the exact amount of time for every car that pulls in. That would be a constant service. The example you're going to see, constant's going to be on Thursday, is this horse for kids at the front of a Kmart or something. And that horse, you put 50 cents in there, it provides ride for the kid the exact amount of time for every child that goes up and puts the 50 cents in. There's only one amount of time. That's called constant. So you got to, when you're reading the problem and it states something about every single customer has, this is the amount of time, exactly 2 minutes for every customer, that's constant. There's only constant, we'll say the word like exactly this amount of time for every one of them. The other ones will give you the average amount of time. But constant will say, it won't say average amount of time, it will be the exact amount of time, because it's the same for every one of them. It's a machine, it's a robot or a machine or something that's automatic. In the old days when you walked up to a coffee machine, it just gave you black coffee. You had to get your own cream and sugar or something like that. And since that's all it gave you, no matter when you walked up and put your money in and hit the button, the same amount of time for every single customer it took for that cup to fill up and for you to pull it out. That's constant. Arbitrary. The big hint to recognize a problem that's talking about arbitrary service, this problem is the only one that will be stating the service variance as a standard deviation or variance. Let me repeat that. Arbitrary service is easy to recognize because it will be the only one, the problem will be the only one that states either a standard deviation or variance of how much the service time varies per customer. So as soon as you're reading a problem and it gives you a standard deviation or variance on the service, automatically go to arbitrary. There shouldn't be any question about it, because none of these other 3 will even mention standard deviation or variance. Just arbitrary. And if the story's saying the service is the same for every customer, you go to constant, because there's no other one that the service would be the exact same for every customer. So that leaves you now with these two. You're reading the problem. It doesn't say the service is the same for every customer. It doesn't say that there's a standard deviation or variance in the service time. You know it has to be one of these exponential, the hardest ones to recognize. And which one is it? It's rather the customers are being served by one service channel, or one teller, or one whatever, or multiple. And then you know which one that is here. And that's how you figure out easily which one of these four formulas you should be using. That's the breakdown that I did last semester. That seemed to help everybody, is how do I get to quickly which formula I should be using. I always start with canceling out formulas. Can't be constant, because the service isn't the same for everybody. It can't be arbitrary, because there's nothing about standard deviation or variance. It's got to be one of these two, and there's only one teller, or one ticket taker, or whatever it may be, so it's got to be this one. If there's more than one teller, or more than one ticket taker, or more than one car wash that a car has a choice to go towards, or more than one ATM machine as the car is pulling up, that's multiple channels, you know that it's this one. And if there's multiple channel, it can only be this one, because we're not going into the multiple channel on any of on these two at all. That's another hint. All right, that's the hardest part. Once you figure out which formula to use, now it's just a matter of taking good notes as to how to use the formulas. So I want to start with this first one. I should have put this up here. I'm going to now. Page 512, because the PowerPoint is screwed up. So I want to make sure you're using the textbook for the formulas on this particular chapter, for the most part. Okay, we're going to demo the first one, Poisson arrival, exponential service. Oh, before I forget, on day one, we're focusing on these two. And we're going to talk about economic analysis for all three lectures, I think. Day two, on Thursday, constant and arbitrary. And day three, this is all about finding the probability of a certain amount of arrivals. And this one's all about finding the probability of a certain amount of service. And then learning how to use Excel and software with these is going to be throughout also. So I'm breaking it into 3 days, 3 parts. This one right here is where most people find it to be the hardest. Calculating these Poisson probabilities, these exponential probabilities. Even though you've all seen this in stats, but it was so long ago, I'm not expecting you to remember it, so I'm going to refresh your memory on how to do this. All right, so page 512. Luckily, in the PowerPoint, these first formulas are pretty good. It's the second one I'm worried about. But I would still rely on the book. 512, there's your formula. I'm going to now jump to right here before we read the story. Right here. Okay. Economic analysis is important, right? We're going to get to that in a second. But there are 6 calculations to be done each one of these service waiting line models. 6 of them. Probability of no orders in the system. And down here, the probability an order must wait. Those are the 2 probabilities that are 2 of the 6. These 2 are average numbers. Average number of orders waiting, average number of orders in the system. And these 1, 2, 3, and 4 that I just told you about are pretty easy. Where everybody starts to have troubles is these 2. Average time in order waits, average time in order in the system. And the reason these 2 are the hardest is because you're calculating the portion of time based on whatever amount of time the arrival rate and service rate represents. For example, let's figure out this one here. Average time in order waits, or average time in orders in the system. Okay, average time in orders in the system, it says 0.1. Everybody got it? Let me go back here. Or let me just stay right here. 0.1. What this means is, it is 10%. The average amount of time an order spends in the system is 10% of the time interval being used for the arrival and service rate. If this is 20 customers on average arrive per hour, that's 1/10 of an hour is the average time the customer will be in the system. If this 20 represents, there's 20 arrivals on average per half hour, that's 1/10 of 30 minutes. And the reason this is important, I'm pointing out the time, these two that are time, is because you have to take this number and convert it to however many minutes or hours or days or whatever by multiplying it times whatever the interval is being used on the arrival. If this is 20 customers on average arrive every 10 minutes, this is 1/10 of 10 minutes, which would be 1 minute. So that's how these two were used. But there's 6 of them. For any of these, you have these 6, and this one right here, average number of orders in the system, is one of the most important of the 6 because this is the number you use to calculate your economic analysis. Right there. Out of these 6, this is the only number out of these 6 that is used to calculate your economic analysis. L. So you've got to understand how to calculate L, average number of orders in the system. And if you look, whoops, if there's a question asking for economic analysis, to get to L, you really only need to do average number of orders waiting, which will then, because you're going to use that number to use average number of units in the system, and then you can stop, because once you have that, you can calculate the economic analysis. You won't need to do these other ones. But if the question's saying, hey, what's the probability a customer is going to have to wait when they get there, then you need to go all the way down to here to do this one. This, by the way, this one and this one are the second most important ones because a lot of companies will focus on, I want the probability of a customer coming here and waiting. Auto supply place. A student was doing a project and wanted to do an auto supply place. He did the calculation and he came up with there was like a 20% chance that a customer walking in, when they finally finish shopping and they get to the cash register, that they were going to have to wait. And they said, you know what, we want to get that down. And that's what a lot of managers focus on. We want that probability to be lower. We want it to be 10% or less. So either we need to open up a second cash register, which is the most obvious way of solving that problem, or we need to do some additional training to increase the speed at which we take care of customers to bring the average customer service rate down. Up, to make it quicker, so that we can bring that probability down. Because a lot of places who do have to provide service say if this probability is too high, we will lose business. It will cost us money. So this is the one a lot of them focus on. This one, the economic analysis, and those two probabilities, especially this one, the probability of a customer or order or whatever this may be, must wait. Okay, let's go to our first example. Joe, we're doing exponential service, single channel. Joe is a stock trader on the floor of the New York Stock Exchange, the firm, blah, 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 blah. Stock transactions arrive at a mean of 20 per hour. 20 per hour. All right, I'm preparing you. What's the probability, or no, I already jumped ahead, forget that. If customers are arriving at 20 per hour, what's the mean or average amount of customers arriving every half hour? That's right, 10 of them then. What's the average amount of customers arriving every, I gotta think a minute, 15 minutes? That's right. You have to keep this in mind. The story may be giving you the arrival rate and service time or rate on one interval of time, but then the question's all about a different interval of time, and you gotta make sure and adjust your arrival and service to the interval of time of the question. Then it says, service, each order received by Joe requires an average of 2 minutes. 2 minutes to process. 2 minutes is the amount of time it takes. It's not a rate. Don't forget, for these formulas, you want to use rates. How many per time interval? Let me repeat that. No matter, arrivals could be given to you in time, a customer arrives every, if a customer arrives every minute, every 1 minute, if that's how it's stated, you got to convert that to how many instead of how much time, or rate. If service is being provided on the average of 2 minutes to provide service, you got to convert that to a rate of how many per interval of time. And then all of a sudden you're reading the question and it says, blankety blank, provide the probability of a customer having to wait on a per hour basis. There, you're given the interval of time. And now you got to convert the amount of time given to a rate. So imagine this. You ready? If the story says it takes 2 minutes on average to process a customer or provide the service, and that service were being provided one customer after another with no break for a whole hour, how many customers could you provide service to in an hour? Exactly. You said it. Thank you. Try to imagine 2 minutes go by, you're helping another customer. You're helping another customer. There's 60 minutes in an hour. You got to convert 2 minutes to a rate of how many every 2 minutes into 60 minutes would be 30 per hour. And that's how you convert it. Now this is I just threw an example out there for arrivals. Let's pretend arrivals were given to you in time instead of a rate. And instead of it saying, you know, I didn't give you a good example of 20. Well, hang on, matter of fact, I will. Let me switch that to 3. There you go. And it could say, calls are coming in every 3 minutes. And the question says, what's the probability of a customer having to wait per hour? You got to get this every 3 minutes converted to how many per hour. So every 3 minutes you're helping a call comes in, one after another. And for a whole hour, 60 minutes, how many calls did you take? 60 minutes divided by 3 minutes for each one is how many? That is how you convert it to a rate. It's how many when you get the time. So we were given the rate on arrivals. I was just converting it to time so you can know what to expect. It could come at you in either way. 20 per hour for arrivals, 30 per hour for service. You ready? The question comes up. Find the probability a customer will have to wait for 5-minute interval. 5 minutes. We got to convert our rate of arrivals to 5 minutes. We got to convert our service rate to 5 minutes. So think this through. 20 per hour, 10 per a half hour, 5 per 15 minutes. There are 3 5 minutes there, so a third of that would be, I think, 1.666 per 5 minutes, maybe? Is it, someone help me out? Is that, if I multiply that times 3, do I get 5? Say it again. Is it? Is that it? Someone take 5 divided by 3. Okay, now let's do this one. What will be the rate that we can provide service for a half hour? How many? 15. What about 15 minutes? 7.5. And now I got to divide that by 3 to get my 5 minutes. Whoops, I didn't mean to put a line there. 5 minutes, 7.5 divided by 3. Now that I don't have off the top of my head. Help me out. 2 point what? 2.13? 2.3? Nobody.
2.5.
Sorry?
2.5.
Thank you. 2.5 per 5 minutes. We would use the rate of 1.66 and 2.5 for arrival and service. And all 6 of these numbers now, all 6 of these will be based on, that arrival will be based on 5-minute interval of time. You will get the probability of no orders in the system will not change. No matter if I use 20 and 30, 10 and 15, 5 and 7.5, 1.666 and 2.5, that will be the same answer. That one at the bottom, probability order has to wait, same answer. Average number of orders waiting, I think is it'll be per 5 minutes, I think. I can't remember on these two. But these two will definitely be different. The average time an order spends in the system doesn't change. What changes is this number will be the amount of time per 5 minutes instead of the amount of time per hour. So let's go here. So right now, this was entered, 20 per hour arriving, 30 per hour service. Average amount of time a customer spends in the system is 0.1. That's 10% of an hour, which is 6 minutes. 10% of 60 minutes would be 6 minutes. It's still 6 minutes. When you cut it down to 5, but what is 6 minutes per 5 minutes interval? It won't be 0.1, it will be whatever that is, 1 point something, right? Again, 6 divided by 5. 6 divided by 5. So the average time a unit spends in the system will instead be 1.2 here, meaning 1.2 of 5 minutes, because we went with we have arrivals at 5 minute interval, and we have service at 5 minute interval. So these 2 times will be the amount of that 5 minute interval. Still trying to give you the same answer. You do the math on it, it will be 6 minutes. But it will just have different 2 numbers here. Let's keep going. Don't worry. By the 3rd lecture, this will all come together. And I would say this would be a couple of lectures you don't want to skip. It'll all come together. Question says, okay, if orders arrive at 20 per hour, which is 1 every 3 minutes, which it could have been given to you that way. Hey, orders or calls are coming in every 3 minutes. You've got to convert it to a rate instead of time. Then it says, therefore, in a 15-minute interval, the average number of orders arriving would be, and we did it right here, 5 per 15 minutes. We just went 20 per hour. That means 10 per half hour. Half of that is 5. We broke it down that way. Now, these next few slides are going into our 3rd lecture. Poisson probability and exponential probabilities, just on the arrivals and just service by themselves. So I'm skipping those, and we're going back to those on Tuesday of next week. And then we're going here. Nope. No, no, no. No. Here we go. What is the average number of orders Joe has waiting to be processed? Average number of orders waiting to be processed. Look at the 6. Which one just got described? Right there. Average number of orders waiting. That's a G, but that's really supposed to be a Q, by the way. L sub Q. Says H1 squared. Take our arrival rate, square it, and divide it by, parentheses, our service rate times service rate minus arrival rate. Divide that into there, you'll have the average number of orders waiting. And sure enough, this is average time. Where is it? Right here. What is the average number of orders waiting? The arrival rate's 20 per hour. The service rate's 30 per hour. We square 20, 400. 30 minus 20 is 10. 10 times 30 is 300. 400 divided by 300. 4/3, what is that? 1 1/3? 1.33. The average number of customers waiting for Joe to get off the call he's on to take the next call is about 1.33 customers. Sure enough, average number of orders waiting, 1.33. Switch it to half hour. 10 squared. 15 minus 10 is 5. 5 times 15. Divided into 10 squared, 100. I'm pretty sure, it's been a long time, but I'm pretty sure you'll get 1.333. Average number of orders waiting. As long as you have the arrival and the service in the same interval of time as a rate, you'll get the right answers. It doesn't matter if you have them both in hours, both in half hour, both in 15 minutes, both in 5 minutes. As long as they're both in the same interval of time, you're going to get the same answers, except for the time, because this could be the amount of a half hour. This could be the amount of 5 minutes. This could be the amount of an hour. And you've got to be prepared to then convert that. Let's say this is an hour interval. It's going to say average time and orders in the system in minutes. You calculate it as 0.1, and you'll go, oh, this is per hour, so you multiply that times 60 minutes. You know that's 6 minutes. Multiply that one by 60 minutes, you'll know what the amount of time in minutes is for that one. Anybody getting overwhelmed? Everyone's okay? Dead silence in here, but we are recording. What's nice is that you can set this up in Excel for the first one. You can have Excel open while you're taking your quiz, and all you would have to do then is plug in your arrival and plug in your service, and all 6 numbers calculate for you. If you decide to use Excel, either you need to write on the quiz what formula you used on the Excel, or just attach the Excel spreadsheet to an email as you're handing in your quiz. And give me the Excel spreadsheet. That's fine too. Now, this next one, multiple channel, you can't set this up in Excel. Part of it, but not all of it. Because the formula, I need to put the pages here, 517 to 519. 517 to 519. The formula for the probability of no units in the system is just too crazy. Oops. Right here. I mean, you can set this up, maybe, but I'm going to show you a shortcut. You're reading a problem. It's talking about the arrivals, and it's talking about the service. Says nothing about a standard deviation of variance. Cancel this out. You can tell that the service is not constant. It doesn't say exactly this amount of time for every customer, so you know that one's out. And as you're reading it, you realize, oh wow, there's 2 people taking care of customers, or 3 or 4. You know it's multi-channel, so you pinpointed the one. Once you pinpointed, now it's a matter of coming up with the arrival rate and the service rate as you read the problem. And then you do not do this formula. Instead, and let's pretend the arrival rate is 20 per hour and 30 per hour on service. We're still staying with those numbers for right now. But you realize it's multi-channel, and you, in order to get your L, right there at the bottom of the page, whoops. The only way to do economic analysis is to get the average number of units in the system, or average number of customers in the system. But the only way to get here is to get this. The only way to get this, because of that, is to get this. So if this is just asking you what would be the lowest cost, the best solution, you've got to do these 3 to get to this so you can do your economic analysis, which we're going to talk about in a minute. So I'm going to give you a shortcut on that probability of no units in the system. Probability of no units in the system means that all the service channels are twiddling their thumbs and they can take a break because no customers are in line to need help. No one's there. What's the probability of that happening? Certain times of the day that could be higher than other times. All history usually gives you a good idea of when to expect these kind of probabilities. So, what I want to do is pretend we have a 20 per hour arrival, 30 per hour service, and we have, let's say now we have a second trader, stock trader taking calls. 2 channels. You're going to go to this chart on the next page, right here on page 519. And instead of doing all that math, all you got to do is take the arrival rate divided by the service rate, and you match it up as close as you can over here in this first column. And then you go over to however many channels exist. 2, 3, 4, and 5 this works for, and trust me, I'm not going to give you a problem with more than 5. And you find the probability, the first answer, of no orders in the system, that nobody's there, that the 2 or 3 or 4 channels get to twiddle their thumbs and have a break. So 20 over 30 is 2/3, which is 0.67, about right here. Does that sound right? Is that 20 over 30? And I said there's two stock traders taking calls now. The probability, now I'm right between these 2, a little closer to 0.65, so I'm going to estimate the probability of no orders in the system. Going straight across to the column with 2, am I there? Is it these 2 numbers right here? I'm going to say, well, it's a little closer to the 0.67, it's a little closer to that than it is that. Let's see, this is 0.48%, 50%, 49 would be in the middle, that's almost 51. I'm going to go with 49.5%. 0.495 maybe. And use chart on page 519. 20 over 30 equals 0.67. Use the column for 2 number of servers, and that's where you got this answer. You're just putting down how you got the answer. Once you have that answer, you go back to the formulas. You can now calculate this, arrival rate divided by service rate to the K is the number of channels, to the power of the number of channels. So I want to make sure this little variable is always your arrival rate, and this variable, if I can draw it right, that's your service rate. That's what these mu and sigma represent, arrival and service rate. So every time, all these formulas are using 3 variables, one uses 4. Arrival rate, service rate, and when you get to multi-channel, you have K, which is the number of channels. The only one that has another variable is arbitrary because it uses that standard deviation. And if you're given a variance, you've got to square root it to get the standard deviation. That's the only other variable involved, standard deviation. And it's only going to be used by arbitrary. So you look on that chart, you get your probability of no units in the system, you plug that in right there, and then here is just arrival rate divided by service to the power of however many channels, times the arrival rate times the service rate. The bottom is number of channels minus 1 factorial, better review factorial. 3 factorial for all those who haven't seen factorial in many years. That'd be whatever number being factorial times every number below it to 1. So this would be 3 times 2 times 1. 5 factorial. 5 times 4 times 3 times 2. You don't have to do times 1, but get it? That's what factorial is. The only tricky factorial, and you will see this on some of these problems, is 0 factorial. It equals 1. That's the only weird one. 0 factorial equals 1. Doesn't make sense, but that's what it is. So it's kind of a only tricky one. So it's number of channels minus 1 factorial. Number of channels times the service rate minus the arrival rate, then square it. Work on your numerator, your denominator. Divide, then multiply times what you just got off that table. Whatever this equals gets added to the arrival divided by service. You have L. You can now do your economic analysis. All right, we're going back to multi-channel. Just a minute. But I want to go to the economic analysis formula. And I didn't write the page number down, but I know it's right here, page 523. There's L. There's the average number of units or customers in the system. It's being multiplied by a weighting cost that will always be given to you in the story. Hey, this company has determined that for every time there's a customer waiting, it has a cost of $20 per hour, or whatever that is. The right-hand side of this formula, K is the number of channels, and that cost right there is what is the cost to add another channel. For example, hey, I have one stock trader taking calls right now. I need a second stock trader. That person's going to be paid $20-something an hour. We're going to have to give him or her benefits, so that's another, $8 an hour, $28. There's the total cost. That's what this represents. Cost of adding another channel times the number of channels. Cost of waiting. The cost of adding another channel will always be given to you. The number of channels will be given to you. The cost of waiting will be given to you. The L is what you have to calculate to do this. Go ahead.
That formula will be the same for all 4 methods?
That is the formula for all 4 methods. What's different about each method is how you get to that L. Nothing else is different between all 4. All the rest is the same. Let's do our cost for the single channel, the trader who's taking those calls. go back to the original, where am I? Where's our little, what's that? Yeah, this is it right here. Okay, you ready? The story says, let me think here. We want to add another trader. If we want to add another trader, I forgot we got the camera here. Let's clear a spot here. I think we're about to get to a story. I think it says $20 per hour to add someone else to take the calls and place the orders. And then it says, if we don't add another trader, every time someone calls and the phone doesn't get answered in time, they're going to call someone else to do their trade, and that other company's going to get the commission. So we're going to lose money. We estimated, looking in the past, of how many jobs we lost and so on, and what it cost us. We think it's going to cost us $15 per hour for any time someone has to wait. And this is to add another channel. Add one channel. Those costs are given to you now. So if we were to add a channel, and we got, I think it was Joe there right now, we'll have a total number of channels of 2. There's our K. Joe's there. We're thinking about adding another channel. That makes K2. What would be our total cost per 1 unit of time if we were to add a second channel? So we got to use the formula for multi, which we'd have to go in the book. Oh, wait. Let's make this easy. We'll do this second. First one is, what's it costing for Joe? Joe's there. It's costing $20 an hour. There's a $15 wait. And we want to figure out the cost with just Joe first before we decide what the cost is adding someone to help Joe. What is K if we're figuring out the cost with Joe by himself? What's K? 1. K equals 1. What is L? Let me go back. What is the average number in the system when Joe's working all by himself? I can't hear you. 2. That's right. So it would be 2 times the waiting cost. 15. We determined it was $15 an hour. Plus 1, because Joe's by himself, times what is the cost of having Joe there? $20 an hour. Our total cost when Joe's working by himself is 20 plus 30, $50, and the 20 and the 15 is the cost per 1 hour. So that's $50 per hour is our total cost. Have them there. And now we go into it, we say, let's calculate now once we get help for Joe. We got help for him. The difference is, yes, this help is going to be $20 an hour also. There's still a $15 an hour waiting cost, but the K is now 2. But the L is different because we have to have 2 instead of 1. And we're using different formulas. Don't think they're the same formula. So there's 2 channels because we got help. We come up with this, we come up with this, we come up with this. Let's pretend we went on the table. We got our probability of no orders in the system. Probability of no orders in the system, I think we did it. 0.49. Let's see if it says 0.49. 0.33. What did we use? The wrong table? What's 30? Oh, I forgot in this story we did some advertising. And the calls aren't coming in 20 per hour now. The calls are coming in faster, 30 per hour. Let's go to our table. What page again? 519. You ready? Calls are coming in faster, 30 per hour. Service is still 30 per hour. You only use the service per 1 channel. This is the biggest mistake. You ready? Oh, we got a second person now. So the service is being provided by 2 of them at 30 per hour. So wouldn't that be 60 per hour? No. You use the service rate per 1 channel. The K takes into consideration that there's more than 1 channel. There could be 3. You're using the rate of service per 1 channel. So it's 30 is our service rate per channel. Our arrival rate went from 20 to 30. So we have 30 divided by 30. Takes us to 1. We're going to have 2 service channels. The probability of no orders in the system, right there. We now can use this number to calculate the next number, the average number waiting. And then we use that number to calculate the next number, which is the average number in the system. And we use that number to get our economic analysis of our cost. Is it going to cost more or less to have that second person helping Joe? Your natural reaction as a manager should be, well, it's definitely going to cost more. We're paying 2 people. But what you don't take into consideration is, if we didn't have a second person, we would have this huge waiting cost. Because the calls are coming in so much faster now with that advertising blitz we did. So let's see what it costs. You ready? We go ahead and we put 0.333 is the probability of orders in the system, and we do our calculation. The average number of orders waiting happens to be 0.333, total coincidence. We use that, we add 0.33 to 30 over 30, arrival rate divided by service rate gets added, so that'd be a 1 added to that. There's our L, average number of units in the system, 1.33. We can stop there because the question says, what's the total cost per hour having both of them provide service with the calls coming in faster now? Same formula, ready? L now is 1.33 times $15 waiting cost, L times the waiting cost, plus 2 service channels instead of 1, times each of them. We're spending $20 an hour on each of them, let's say. Now add this up. 20 times 2 is 40. 1.33 times 15, a third of 55, that's 20 also? Is that right?
19.95.
Okay, I'll call it 20. 19.95, really? Darn. 95. Okay. Add that up, I get 40, I get $59.95 per hour. Should we, look at the cost per hour and the cost per hour. Should we do our advertising blitz, which will increase the amount of calls coming in, and should we hire a second person? Are we saving money, or is it costing us money per hour with the new system if we bring on a second person? More or less?
It's more.
So, yes, we have to determine what happens if we brought in a third person. What if we bring in a third person? Nothing else changes. We would have to recalculate our L. The cost per waiting doesn't change. The cost per service channel doesn't change, still $20, but instead of a 1 or instead of a 2, that would be a 3. So a different L and a 3. And we would come up with a total cost per hour then and figure out. And what will happen in most cases, I have to jump over here, is that you'll find your cost per hour is like up here. And you're going, okay, the calls are coming in so fast, we got to have a second channel. And you brought your cost per hour down because maybe that cost of waiting is so expensive. By adding a second person to take calls brings your total cost down. And then maybe adding a third person brings it down. But then you realize if you add a fourth person or a fifth person, the cost starts going up. It's almost always like a U. And all of this work you're doing is to find that point where the bottom of that U curve is, because that is the perfect amount of service channels. This will provide the customer service you're looking for, at the same time stop wasting money on having an overkill of channels. That's the economic analysis does for you, is find the perfect number of service channels that will keep your overall cost as low as possible and still provide good customer service. Now, some people say, I still want to spend a little more, even though it's going to cost me more per hour, because I need to bring that probability of an order having to wait down. But this still should be, if the probability of an order having to wait is so huge, then the cost involved of a person having to wait will be higher than average. And that will automatically take that into consideration and still bring you to the perfect amount right there at the bottom of the trough, at the bottom of the U curve. That's the perfect amount that you should schedule for service channels. And that's what this is all about, is to find that optimal amount of service channels to schedule as a manager, so you're not wasting money and doing an overkill, or have too few and losing money because customers are leaving because they have to wait so long. It's that spot. That's what this does. And that's why the economic analysis is so important. And it's used on all four of these. All four of these, you just have different ways of getting to the L. And then you use that to calculate your economic analysis. All right, so let's go to the story now on the second one. You ready? Is this the second one? Multi-channel? It's last one. Yeah, it's got it. So the company said, we're going to do an advertising campaign, and we believe it will increase our business by 50%. Calls are coming in at 20 per hour, but it's going to increase our business by 50%. So now calls are going to come in at 30 per hour. Joe can still help them at 30 per hour. But if you have only one person that can help them at 30 per hour, calls are averaging coming in at 30 per hour, that's unsolvable. The arrival has to be less than the service unless you have multiple channels. But 30 arrival, 30 service, you'll try to solve it using the software, try to solve it using Excel, no answer. It's impossible. Joe will be overwhelmed because if the average is 30, that means there'll be more than 30 coming in at times, which will cause a backup. Well, even when it slows down to where less than 30 an hour calls are coming in, they're still going to be backed up because of the initial backup that takes place when more than 30 come in. So you have no choice. Once you have a 1-to-1 ratio, 30 coming in, 30 per hour being helped, you have no choice but to add a second channel. Or you're just asking for a ton of waiting costs, losing customers, offending customers, or whatever that may be. So they're coming in now at 30 per hour. And to handle this increase in volume, we hired an additional floor trader, Fred. He works at the same speed as Joe. And the cost, same cost, the cost is going to be, you got to go to the next slide, or does it say it? Doesn't say it? Where does it say how much? I don't know. What will be Joe's alone, why will Joe alone not be able to handle the increase in orders? Since Joe processes orders at 30 per hour, and the arrivals are going to be 30 per hour, the arrival rate and service rate are going to be equal to each other. Once you have a utilization factor of 1, you can't handle it. You're going to have backup no matter what, because that's just the average. There's going to be times where calls are coming in a little more than 30 per hour. And as soon as it gets over 30 per hour, you have a backup that will never be caught up. It won't be ever caught up. So this implies the queue of orders will grow infinitely large, hence Joe alone cannot handle this increase in demand. So what's the probability that neither Joe or Fred will be working on an order at a point, which is no units in the system? We're using the multi-channel. We went to the chart. That's that very first probability. Probability that no orders in the system and Joe and Fred could play catch. Bring out the gloves. Let's play some catch until the call comes in. The probability of that, we go to the chart. 30 divided by 30 is 1. We go to 1 over to the 2-channel column, and we found a probability of 0.333. Or, here's the formula. You can do all of this, same answer, 0.333. Chance, there's a 1/3 of a chance of them being able to grab a bite to eat, go have a smoke, whatever it is they do. What is the average turnaround time for an order? That's the same as saying average time in the system. And by the way, on a quiz, it will be more clear. It will be more like words like this. The same words out of those 6 calculations, I'll probably use very similar words. Average time in the system. Average number in the system. Average number waiting. Instead of things like, I found early 8 years ago, 10 years ago, what is the average turnaround time? People had confusion as to, okay, what is really being asked here? The average time in the system is really being asked, but I'm going to try to make the words very clear to where you don't have to spend time trying to figure out what's being asked for. So what's the average time in the system? That is, if you go to look at your formula, average time in the system is the variable W. Since this is multi-channel, the average time in the system's right here, but the only way to get that is to find the average time a unit spends waiting, and the only way to get that is to have your L sub Q, which is the average number of units. Whoops, where's my LSUP? Average number of units in the waiting line. You gotta have that to get to these other ones. Just like you have to have it to get to L. So we calculate that. L sub Q we start with 30 arrival, 30 service. 30 arrival, 30 service, squared. 1 factorial because there's 2 taking the calls now, minus 1 makes 1 factorial. 30 arrival, or service, 30 arrival, 2 times 30, minus 30, squared, times 1 factorial. Take the whole thing, multiply it by the probability of no orders in the system, 0.3333, and you end up getting 0.3333. We use that number to get L. 0.333 plus 30 over 30 is 1.333. We used it to get our economic analysis. But the question's asking the average time. Take our L, which is 1.333, divided by our arrival rate, so 4/3 divided by 30, 4/90 of an hour. You take 4/90 as a decimal, multiply it times 60 minutes, 2.67 minutes. But if you, this is what I was talking about, where you get 0.1 or 0.03, and then you multiply it times whatever the interval of time the arrivals and service are, 30 per hour. So that's 4/90 of an hour. 490 times 60 minutes is 2.67 minutes. So what was that? The average time, we were doing this one or this one? Was it this one? So that's 0.044. If you multiply that times 60 minutes, it should be about 2.67 minutes. I think if that's the one we were doing. Looks like it would be. Everybody get it? How are we doing on time? We got 8 more minutes. I'm going to do a quick demo. Here we go. Let me get to the software. Are we on the screen? You see this? Okay, you ready? Waiting line, number 9. Let's call it new. Which one were we just doing? Let's see, we got arbitrary single channel. Wasn't that one. Deterministic means constant. It's another word for constant. We weren't doing constant. Arbitrary, no waiting, forget about that one. We're not learning that one in this semester. Exponential service finite, we're not learning that one. Exponential, we're single channel, multi-channel. They're both in one right there. And that's what we were doing, was multi-channel. So we'll go with that. Now it wants to know how many channels. Well, there's Joe, and we brought on Fred. 2. What's the arrival rate? After we got done with that advertising, it went from 20 per hour to 30 per hour. What's the service rate? 30 per hour per channel, right? Because it's only per channel here. And they each can help customers. Let's go to the economic analysis. The bottom one is the easiest one. Cost for a channel. We got both of them in at $20 an hour with benefits. Total. So 20. Cost of waiting. What do we use for cost of waiting here? 15? We'll just pretend this is our cost of waiting right here. 15, right? Is everything else the same? So if I'm doing this right, should it come out to this? Did we use 30? Is 1.33? Yeah, it is, isn't it? So let's make this 15. Now this doesn't say cost of waiting. It says cost per time period, in this case per hour. For units in the system, that means units sitting there waiting, and then the time it takes in the system. So this would be $15, I think is what I said, hypothetically. So if I did this right, when we get our total cost, it should be $59.95. Does that sound right? Per hour? Solved. Okay, that's why I was wrong. Darn. There's 0.33. We looked. Remember when we used that table? There was 1/3 of a chance, probability of no orders in the system, and Joe and Fred could break out the gloves and play catch. The average number of units waiting, 0.333. We calculated. Remember, and then we had to add it to 30 over 30, which is 1, to get our L, average number of units in the system, 1.33, which is what we used to get that total cost, economic analysis. This $60 is that 1.33 times the $15 per hour waiting cost, plus 2 employees, where's K, 2 channels up at the top there, times $20 an hour for each one of them. Add that up, it's $59.95 or $60 an hour. Wait a minute, let's go back. Edit. Hey, I only want Fred to work. But look at the arrival, 30-30. It's going to tell you. Can't be solved. You cannot, there's no way one person can handle 30 calls coming in when their average rate is 30 per the same amount. So let's say we didn't do the advertising. They're coming in at 20 per hour. If this worked right, we should get a cost per hour of $50, right? Because now it's, our L is going to end up being 2, you'll see, times $15 an hour. We're saying Joe's all by himself, times $20 an hour. This should come out to $50. And nothing else changed other than the arrival rate. We're pretending we didn't do the advertising. Sure enough, here's our L, 2 times the $15 an hour waiting. Joe by himself is $20. Added together, $50 per hour. I want to do one more. We're going to add a third person. Go back to edit. We did the advertising. They are coming in at 30 per hour. We decided to go with 3 people instead of 2. $15 an hour waiting cost still, $20 an hour for each one. We're paying 20, 20, and 20. We're going to have a different L, but it's still times $15. 3 times 20. Our L is now 1.0455 times $15 waiting, plus 3 times 20, which is 60. Our cost per hour is $75.68. What I want you to notice, though, is look at how low our probability is of a call coming in having to wait because we have 3 there now instead of 2. The probability is down to less than 10%. That's still a 9% chance of someone having to wait. That's still kind of a big deal. So this may be worth the extra $15 an hour to bring that down. And then we do it again with 4 and see where we end up. Nothing else changes. Switch it to 4. That's what's nice about the software. Now we're at $95. Okay, well what happens if we go with 5? Now we're at $115. As you can see, we're already past the bottom of the arc, and we just keep going higher and higher, which means these are too many employees for that many calls at that rate. With if your waiting cost is only $15 an hour. Now, if we increase that significantly, where we know if someone has to wait, they're going to someone else, then you will see that 3 may be the perfect amount instead of 2, or 4, depending on what that is. All right, this was an intro to it. If it's slightly overwhelming, don't worry about it. We're going to put it all together by the time we get to the 3rd lecture, where it won't be so bad. I'll see you on Thursday.
I was just looking at this and I was a little bit confused.